Our model is a simple one. Energy is conserved. The total amount of energy in the universe is constant. If I heat this up, if I add heat energy, heat this up to make a liquid out of it, out of the argon, then that energy came from somewhere. Something down here had energy, and I've transferred that energy in the form of heat energy transfer. I've transferred that energy up to the gas. Total amount of energy remains constant. Whatever energy left this thing down here is the same as the energy that showed up in the gas. So in our model, we first choose a physical system, and then we think about how to describe the interactions. And there's two kinds of situations that we can choose. We can choose to talk about different things in different ways. One is a closed system. If the system is isolated from its surroundings, then we call it a closed system. If it's isolated, then its energy can't change. So the total energy at the end, E final, E sub F, is the same as the initial total energy, E sub I. E sub final equals E sub I. Final equals initial. That just says that we have a closed system. No energy is being exchanged. I haven't turned on the heat. I haven't turned on cold. I haven't pushed down on this, which is another way of exchanging energy. So no interactions with the outside are exchanging any energy. So E final minus E initial is 0. E final minus E initial, we call that the change in the energy. This thing has energy, but it's not changing. So the change in the energy is 0 for a closed system. Now, for an open system, open physical system, it interacts with its surroundings. If I turn on the heat, if I turn on this flame, I'll transfer heat into it from the surroundings. So that's an interaction with the surroundings. What will happen? Well, you already know the temperature will go up, and that's an indicator that the thermal energy has gone up, and that will mean the total energy has gone up. So E final minus E initial is going to be positive. If I add energy to this, right now it's sitting at 91 Kelvin. If I turn on the flame, I add energy to it. Now its energy is higher, so E final is larger than E initial, so the change is a positive number. So Q is called heat. Q is our measure of the amount of heat added to the system between the final and the initial states. I added heat, therefore I raised the energy, so delta E is positive. If Q is the amount of heat added, then I added heat, then Q is a positive number, so I have a positive on the right and a positive on the left. What if I took heat out? Then the total energy goes down. So E final is smaller than E initial, so this is going to be a negative number. Delta E is going to be negative if I've taken heat out. If delta E is negative, Q, remember, is the amount of heat added. If I took heat out, if I did not add heat, but I took it out, then Q is a negative number. Q is negative, delta E is negative. This still makes sense. I left something out in the possible interactions, and that's W. We'll talk about that a lot later in more detail, but I'm going to mention what it is right now. I'm going to heat this argon up to make a gas. I'm going to boil, in other words, the liquid, and turn it into a gas. Just to show you what work is. Work is a different kind of energy transfer. It's the kind that happens when you change a macroscopic variable. For instance, there's a volume to this container. I can change the volume by pushing down on it. In thinking about work, we're calling work an energy transfer. Heat was an energy transfer. If we transferred heat, the energy inside was larger. We saw the temperature rise. Let me transfer work. Let's see what happens to the energy. Let's see what happens to the temperature. If I push down on this, temperature right now is 238. If I push down on this, if I transfer work energy, the total energy can go up, thermal energy can go up. Notice the temperature went up. So transferring work is another way of transferring energy, just like transferring heat can transfer energy.